the topic of my talk is turbulent energy flux and drag reduction in MHD turbulence. So I will just show you what is drag reduction in this talk in MHD. And this paper is published recently. And my collaborators were Sadab Alam and S. Chatterjee. So turbulent drag reduction. So what is this phenomena? So this is known for more than 70 years. So in a pipe flow, this is a pipe and water is flowing in the pipe and we put in some polymers. Once you put the polymers, then it turns out, so without polymer, the black line will be the velocity profile. It's like, it's not, I mean, it's a turbulent flow. So it is not parabola, but this black line is a turbulent profile. But as soon as you put polymer, then green line is a turbulent profile. So the mean velocity is increased when you put in polymer. That is the drag reduction. So basically, the people who are firefighters get advantage of this because mean flow is faster. So in fact, without polymer, it would, let's say, go to 10 meters. With polymers, it can go to 13 meters. So this is what is used by, in fact, firefighters for using in fire hoses and also in pipes. Now, the one question is it the bulk phenomena or boundary layer phenomena? People believe that both are important, but in this talk, I'll just focus on bulk. I will not have any walls, and we'll just focus on the bulk properties of MHD turbulence. And I'm going to show you that similar phenomena does happen in MHD. Okay. So MHD has similar features, but before we go to MHD, we need to define what is drag reduction. What is turbulent drag? So I will go slowly, and we first try to do hydrodynamic turbulence. So let's look at the Navier-Stokes equation, which everybody is familiar with. So this nonlinear term, U dot grad U, is the drag. You know, this is the force. This, in fact, is like a drag force which we experience. And this also is responsible for energy flux. You know, energy goes from large scale to small scale. So this term is what is responsible for drag. And we'll estimate this term without magnetic field and with magnetic field. Okay, and that's what we'll see. Other terms, so we can just analyze them. So in Fourier space, so I'm going to work with Fourier space for reasons which is going to become clear soon. So Fourier space, the velocity mode evolves like this. This is a nonlinear term, and this is a pressure term. Okay, so nonlinear term is a convolution, right? So UP, UQ, and K comes from that divergence term. Now, of course, we force this flow with a large scale. So this is important to keep in mind that I force it by large scale. So in a pipe flow, we have pressure gradient, at large scale pressure gradient. So energy supplied at large scale by this FLS, force at large scale, goes to intermediate scale and small scale. So there's energy transfer. So there's energy transfer formula, which I'm going to use it. So UK mode, this UK mode, which I'm using the mouse, is getting energy from in a triad. So we focus on a triad. So the triad is a basic unit. Energy flows from two Fourier modes, UP and UQ to UK. This is a bit technical, but I just want to explain this important thing, which is not fully related in some sense, but I will just show this. So energy formula from velocity field, I can get energy equation. And for a single triad, so we have UP, UQ, and UK, and this is a formula for a single triad energy transfer. Now, so there are two terms, UP gives energy to UK and UQ gives energy to UK. So these are all included here. But it turns out for our derivation of energy flux or energy transfer, we can do even better. And so the formula is called SKPQ, it's called mode-to-mode transfer. And this is a formula which is, I think, this important formula, which unfortunately not many people have seen it. So we can derive for hydrodynamic turbulence how much energy goes from UP to UK. So this P is a giver and this K is a receiver. So UP gives energy to UK, and this is a formula, you know. So and here UP is a giver mode and UK is a receiver mode, and you take a dot product with a mediator. So mediator is like a lawyer, and here the UJ is like a mediator. So these are nice description in Fourier space for getting the energy transfers. And with these formulas, we can compute. So this is their part of a book which I wrote recently. So this is an advertisement. Now, so we can get energy flux. So what is energy flux in turbulent language? This was the talk just before my talk by Berenguer. So the energy flux is energy going from all the modes inside the Fourier space, Fourier sphere. So this this yellow sphere, this is a 3D sphere, and modes, all the modes inside the sphere gives energy to modes outside the sphere. So because of nonlinearity. And this formula, I mean, this flux we can compute easily, which is not done often, like, but in the last talk, she was telling about the last plenary talk. So this is energy flux formula. So all the modes inside the sphere, which is U less, which is here, gives energy to modes outside the sphere. So this is the formula given by this. And so we can compute them in numerically. So we just, or even analytically it can be done, but we'll focus on basic properties of this in this talk. And there are other formulas, but I'm going to use what I just said by in terms of this mode to mode transfer. So P is the giver. So all the modes inside the sphere are giving energy to modes outside the sphere. Now, Kolmogorov theory, in fact, follows. In fact, in the last talk, there was a question that why is the flux constant? You know, so or why is spectrum is k minus phi third? In fact, you can see from here by one simple argument in Fourier space. Of course, it doesn't answer all the questions about singularity, but it is very nice because this flux can change only by if I give some energy at intermediate scales. This is important to know that if there is some energy going into intermediate scale, that is FLS here, and there's a dissipation. So if Kolmogorov assumes that energy is supplied only at large scale, so Kolmogorov assumes that there's no energy supply in the intermediate scale and there's no dissipation in the intermediate scale. So this d pi by dk is 0. So flux is constant. Now, of course, this is a mean, huh? So the flux can fluctuate a bit, but the mean flux is constant. And if this is constant, then by dimensional analysis, you can derive k minus phi third. And this has been, so this is a picture I'm trying to show, that this flux in the inertial range is important for me to derive drag reduction. So this is key part. So flux in the inertial range is constant for hydrodynamic turbulence, where the forcing, which is the red sphere here, small v number, is giving energy at large scales, supplying energy at large scale. So it could be like a bucket of water. I stir with a big spoon, you know, a big stirrer like that. So flux is constant for inertia, and this is verified in many simulations. This one such simulation I'm showing you. So this is normalized. Well, this flux is constant here. You can see that in wave number space, flux is constant. Of course, dissipation range flux is not, it decreases, but in the inertial range, the flux is constant. Now, what is turbulent drag? For hydrodynamic turbulence, without polymer, no MHD. So I can just define that F drag, D for drag. Huh? So FD hydrodynamic, this HD is hydrodynamic, is a nonlinear term. I do RMS, U dot grad U, RMS. I put a mod. And this is like, so under steady state, the external force will balance the nonlinear term, right? I mean, because these are large scale forcing. So at large scales, the external force, which is the stirrer doing like this, which will balance the nonlinear term. Now, from dimensional analysis, you can see that I can multiply. So one more step, I multiply by U here and in the full equation. Then I find that that is the flux pi U. Pi U is energy supply rate at large scale, U times turbulent drag, which is energy supply, which is here, the two U's, but I put one more U, so U cube by D. So we can estimate the drag to, the energy supply rate by U cube by D. So now I divide this equation by U, so my drag will be U squared by D. So the key idea for this talk is that my turbulent drag is flux divided by U RMS. That is what I'm trying to do. So I compute the flux and divide by large scale velocity, and that's how I'll get this turbulent drag. Now, what happens in MHD turbulence of polymers? I'm going to show you that pi U will decrease with wave number. Okay, And as a result, the flux is lower in MHD compared to hydrodynamics. So the drag is lower. And the same thing happens in polymer. So that is the main objective, which we will do it in this talk. So, so I hope this part is clear. So let's summarize. So we compute the nonlinear energy transfer for hydrodynamic turbulence. That gives this cascade of energy. And given the cascade, I divide by U. So that will give me the turbulent drag, which is same as the well, the force at large scale. Okay. Now, MHD equation in this audience, everybody knows about it. So here, but let's just summarize it. So this is a Navier-Stokes equation, but we have additional term in this equation, which is this B dot grad B. It comes from Lorentz force, J cross B. Okay, so this is an additional term. Otherwise, the equation is exactly the same. Pressure is modified a bit by magnetic field, but we just focus on this B dot grad B term. Or we have an additional term is B dot grad B. And normally in MHD, we force at large scale. You know, in Dynamo, we're supposed to force large scale by some stirrer, or in astrophysics, supernova is supposed to be doing that stirring. And magnetic field also has an equation, which is dV by dt, and there are two nonlinear terms for magnetic field. Okay. Now, we don't need to worry too much about this viscosity and resistivity. It's not quite important. We focus only on the nonlinear term. In fact, for this talk, I'll focus only on the top equation. So the difference between Navier-Stokes and MHD is that we have this new term B dot grad B, which will change the nature of energy transfer. Okay. So this is what we have. So so I just want to take a detour. So there's a bit of time. So I want to, so I don't talk about energy spectrum. I don't really need it for this drag reduction, but I just want to advertise one more result, that what is the energy spectrum? Is it 5/3 like hydrodynamic turbulence, or 3/2, which was a spectrum proposed by Kricknen? Okay. Now, though, so hydrodynamics is 5/3, everybody believes it, and it's seen in simulations, experiments. But in MHD, these are the two competing theories. Now, this was second later. 3/2 theory came by Kricknen first. Kricknen and Ereshnikov, these two scientists. And this way back in 64 and 65. These are papers written at the time. And they argued that the time scale is not nonlinear time scale coming from U dot grad U or B dot grad B, but it comes from the mean magnetic field, V naught. And the result, the energy spectrum is not Kolmogorov, but it is minus 3/2. So this B naught has come into play, and that alters the spectral index. Now, it turns out, well, I mean, there are some people who believe that 3/2 is correct theory, even now. But I am a believer that 3/2 is not a correct theory. And there are observations which show 5/3. Though there is no conclusion at this point, which is agreed upon by the whole community, 5/3 is a strong candidate. And the reason why 5/3 happens, it has been a puzzle. And only some 20 years back, this puzzle was resolved. And one of the theory which I did was that Kricknen is correct that B naught is responsible for giving the time scale, but he made a mistake that this B naught, which is a mean field for the whole box, but the idea is that this alphane wave of small wavelength here, it is riding on the large wavelength alphane wave. So this B naught is not, for example, I give an example of if I'm going on a mountain, I don't see the mean slope of a mountain, but I see local terrains, local terrains. So a small wavelength, sorry, alphane wave of a small wavelength sees alphane wave of a larger wavelength, and that sees even larger wavelength. So the B naught, it turns out, is function of K. It's I could show it mathematically, is function of K. Now, in Kricknen formula, we should substitute this B naught. We should not assume B naught to be constant. And if I substitute it in this B naught, you just plug that in and we recover 5/3. Okay? So it's a kind of magic, but this is what is one picture that 5/3 comes. And this resolves why we get 5/3, even though B naught does play a role. Anyway, now let's get back to, these are the papers published on this. Now let's get back to flux. So that was spectrum part, but let's get to flux. For MHD, there are lots of fluxes. In fact, there are, so every term gives different kind of energy transfers. So this U dot grad U is usual hydrodynamic U to U transfer. Then we have this term, which is B giving to U. So there is energy exchange with energy transfer between U and B. Okay, so this term is responsible for that one. And magnetic energy also has energy transfers. Of course, these formulas look very complicated, but if you just spend some time on it, it's quite easy. And this is the picture for energy fluxes. So we have this velocity sphere. So these are wave number spheres. Huh? So there, all the modes inside the yellow sphere gives energy to modes outside the sphere. This is Kolmogorov flux. This one U dot grad U. Now there are energy going from velocity field, this one, to magnetic field here. So this is magnetic sphere. Huh? So there could be energy going from here to there or here to here, and so on. Okay. Now there are 6 of them. There's 4 green arrows, 1 magnetic field, this flux red arrow, and 1 blue arrow. So Kolmogorov has only 1 blue arrow, one arrow, this blue arrow, which is energy going from small wave number to large wave numbers. But MHD has more complications. Okay. Now these green arrows are responsible for energy transfer from U to B. And it turns out the dynamo is basically occurring because of the green arrows. So large scale magnetic field, here large scale magnetic field, which is wave number small, is getting energy from large scale velocity field by this. So this large scale dynamo, small scale dynamo. So we've done a lot of work on this, but this is responsible. Now, it turns out the pi U, which is constant for Kolmogorov flux or hydrodynamic turbulence, is not constant for MHD. And why not? Is following reason. So here in this, let's think of a shell. This is the important picture. Huh? So please focus on it. So this yellow shell, this shell, this is basically a shell with modes. So it has some forcing. Hydrodynamic turbulence, there is no forcing in the intermediate scale. But here, the Lorentz force, which is active at all scales. So the blue wheels are like Lorentz force, J cross B, which is forcing the flow. Now, as a result, the flux will not be constant. And we can derive it. The change in flux, this pi, from one sphere, from one radius to other radius, is difference between energy supplied by the Lorentz force and dissipation. Dissipation can be ignored in the inertial range, but this energy supply rate by the Lorentz force is non-zero. Okay, and it turns out under most situations, under steady state, most situations, this is negative. So because magnetic field takes energy from velocity field, this Fu is negative, so pi U decreases. So here the pi k plus dk will be lower than pi uk. Okay, so that is a key aspect. Okay, now I will show you some proof from shell model demonstration, but let's just think of the key idea. So for MHD, so this is a Kolmogorov picture where these 2 fluxes were constant. They were equal, so not equal. But here, because of forcing inside, I didn't draw the picture here. We were forcing inside the shell, flux decreases in the inertial range. And that is what is responsible for dynamo. In fact, there's red arrows. So my color has changed, I'm sorry. So these red arrows are energy representing the energy going from velocity field to magnetic field. And this is responsible for dynamo. Okay, so what is the difference? Here pi U, this blue arrow will decrease with wave number. Here it is constant. Okay, so that's a key difference. Constant, not constant. In fact, it's decreasing. Now, so if I look at kind of lower sphere, large scale, so remember the drag is basically at large scales, the turbulent drag. So that large scale sphere, at that the flux at basically low wave number of MHD will be lower than flux for hydro. I hope all of you will agree with that. And where has the remaining flux gone? It has gone to the magnetic field. So this red has taken some of this energy. Okay. Now, so how do I get the drag reduction? Now for drag for MHD will be FD comma MHD. Okay. Now I need to compute the U dot grad U LS. And that is basically, I compute the flux by U. Now this flux for MHD is lower than flux for hydrodynamics. So if I have the same injection, like if I do a hydrodynamic simulation with epsilon injection in energy supply rate, this one, so I get FD. But now for MHD, it will be injection minus the energy going into B field. So this upper, the numerator is lower for MHD compared to hydro. So FD MHD is lower than FD hydro. Okay, so these are the two formulas. For MHD we have this. For hydro HD we have this. So clearly this number is bigger than that number. Okay, so that means FD MHD is lower than FD HD. So there's a very simple idea coming from flux, and because magnetic field is taking energy from velocity field, it decreases the flux, and that leads to a lower drag. So, and the same thing happens for polymers. Polymers, in fact, is known. I'm not saying it for the first time. Polymers are like magnetic flux tubes. They take the energy like spring, you know. So springs do take energy just like magnetic field, and very similar thing happens in polymers. So flux tubes are like polymer chains, and that is like magnetic field. So magnetic flux tubes are analogous to polymer chains, to at least qualitatively. Even quantitatively, there are a lot of things just translate. Now, so this is universal drag reduction. That's what I'm trying to get to. Now let's try to see whether we see this in simulations or so. DNS we have not done. Well, we've done simulation, but not looked at this aspect. Shell model was cheaper, so we did shell model. So this is shell model. There are a lot of shell models, but this is one we constructed. Is there in that physics of plasma paper. I will not detail this, but please look at this picture here. So the solid lines are MHD flux. So look at for one particular injection rate. The blue is injection rate of 0.1. So hydro will be above. So these are nonlinear. So this is flux pi U we computed by nonlinear stuff. And MHD is solid line. So you can see that there's in fact drop by around 50% drop. So flux has shrunk in MHD compared to hydro, and it happens for different injection rates, and we see it here. Okay, so flux is decreasing for injection rate here. So you can just compare the number 0.1 for this one, and here is 0.02. MHD has dropped by factor 5. Here, factor 5 in fact, flux. Now, this is interesting thing which I dug out this simulations, old simulation, and we find that in Dynamo, when magnetic field turns on, the magnetic field is just EB is turned on. So kinetic energy also gets a jump. So it's somewhat surprising. If you think that if magnetic energy is more, the kinetic energy must be suppressed. But no, kinetic energy also gets a jump. It's like in a polymeric flow, the velocity field is increasing, the mean flow is increasing. So I need to rush up. Similar things happens for liquid metals. I can show that when increase the magnetic field, in fact, interaction parameter, my U is also increasing. Now I just want to flash this slide. Nonlinear term is decreasing, right? I just showed the flux is decreasing, but mean flow is increasing. U is increasing. URMS or U is increasing. So that looks surprising, but it's not so. Because U dot grad U is not just U squared by L. There's a factor which comes from phase correlations. You know, so it's a kind of correlated flow with polymers and not so correlated with magnetic field, and that this factor is important, and this factor is what is causing drag reduction. Now, so I hope this is a key part. So we should not simply dimensional analysis say U dot grad is U squared by L, or energy supply rate is U cube by L, which is not the case. This factor is what is important, and we can pull it out. So even though this term is for hydrodynamic turbulence, there's no factor is 1, but for polymers the factor is less than 1, maybe 0.5, 0.2, like that, and that is why the drag is reduced. Okay, so these are all these details you can find a lot of it in this new book. And so my conclusion is that turbulent drag is in MHD turbulence is weaker compared to hydrodynamic turbulence. And very similar things happens for polymer, which has been studied. There are 1,000 papers or even more than 1,000 papers in that field. And similar things could happen in hydrodynamic, like rotation or some other phenomena, which we have not studied it. But, and okay, I thank you for your attention.